So the first session will be Liz Moyer and Roy Rao Kotamarthi, Liz from University of Chicago and Rao from Argonne. And then we'll go later this morning to the second session, which will talk about complex systems and silos, and Pam Sedelko and Don Woobles. And finally, 1 o'clock this afternoon, Tom Wall from Argonne will talk about adapting to climate change. So I think it'll be a very interesting day, a bit more free form perhaps than some of the other days, in the sense that Liz and Rao have minimized the number of slides and they're maximized the time for questions. So open your put on your thinking caps, and based on what, they'll each have about 5 minutes or so at the beginning to stimulate some questions, but think about those questions. And I will tell you, both of these folks, Liz and Rao, are very good at answering questions. They are experts in their fields. So I think you're going to enjoy this. Let me introduce both of them. Liz is studying the distribution of water vapor and the formation of cirrus clouds in the atmosphere, and especially the use of a new tracer of convection and condensation, the isotopic composition of water. She's a member of the CIM Earth project that involves researchers in climate modeling, economics, law, computer science, numerical methods, statistics, and human behavior to build open source models and tools. They're publicly available to everyone. They're currently developing new climate emulators using artificial intelligence, I suppose, to provide information from full general circulation models to integrated assessment models used for policy analysis. And you can ask her, if you like, exactly what that means. Rao Kotamarthi is chief scientist and department head at Argonne National Laboratory's Atmospheric Science and Climate Research Group. He also has a position at the University of Chicago, senior fellow at the Computational Institute, and is a member of the Energy Policy Research Institute. Rao has 30 years of experience in regional and global scale climate modeling. His research is funded by DOE, it's funded by private sources, also by NSF. And he has contributed to the IPCC assessment report too, serves on lots of review panels, peer review panels for DOE, NSF, and NASA. So let's see, who'd like to go first? Rao, would you like to take 5 minutes?
I'm ready.
Off? Okay, great. It's all yours.
Okay, thank you. Thank you for the invitation, George. And I would like to start by kind of trying to give a little bit of history of climate modeling. So climate modeling, as we know, kind of understand today, is actually maybe a 19th century construct in some sense. A guy named Arrhenius actually used a 0-dimensional box model to calculate what would happen to Earth's surface temperature if we were to double the amount of carbon dioxide. He came up with a number about 4 degrees centigrade, which has been quite robust as we went into late 20th and 21st centuries, actually. And the type of models that do this, that actually started from there, and maybe Manabe, developed by Manabe later on as a 3-dimensional models. These are what is known as energy balance models. So what the main purpose of these models is to do the energy balance of the Earth system. So where is the energy absorbed, where it is emitted, what goes up into space, and what comes at the surface. So there's a lot of time spent on trying to perfect these things, and the models over the years have actually evolved over using this energy based this concept that I want to get the energy budget of the Earth as best as I can. So as we started learning more about the Earth system, people decided that you need aerosols in it, you need clouds in it, you need water vapor in it, not just carbon dioxide. You have to do radiative transfer through the atmosphere in a column, but also that energy transfers horizontally across the globe. So you have 3-dimensional models developed as a result of that. Then we started thinking that, okay, the biology of the Earth has a role to this, including ocean. So what is the ocean biology and ocean, the energy properties of the ocean, the biology of the ocean, the biology of the Earth. So slowly you've included plants and other things. So it's right now, models, we call them have evolved into fairly complex system models, which include both the atmosphere, through which the radiation happens, the sun, of course, and then the surface, the plants, the oceans, everything you can think of on this planet and is included. The one interesting thing that happened over the last 20-25 years is trying to simulate the carbon cycle of the Earth. So once you started thinking about the carbon cycle, then you needed to include the vegetation and what happens to vegetation or seasonally and things like that. So right now, the Earth system models, the so-called Earth system models, are both to the energy balance and the carbon. So to do carbon correct, you need nitrogen. So there is a nitrogen budget in these models. So and now people are including phosphate because phosphate is another important element that controls nutrition. So slowly it has evolved into the system model, and we are at this place where there are really fairly complex models that simulate the Earth system's energy balance to the best as we understand right now. A lot of interest in clouds and how clouds react to aerosols because they're very sensitive. What happens when you have wildfires and they emit aerosols, and the aerosols change some of the energy characteristics and they transfer to the atmosphere when you have a lot of these aerosols. So this has been the arc of the developing of the Earth system models. But of late, there has been a lot of interest in trying to understand how humans are impacted and how humans impact the climate. Of course, a lot of the interest in climate is because of the anthropogenic emissions we are experiencing right now. Anthropogenic meaning humans using fossil fuels and giving carbon in the atmosphere. So how does that change the atmosphere, the radiation budget of the Earth? And the second question is, how does the changing climate affect the people? So both of these questions require that some aspect of people be in the model. So this is a challenge we have right now. Essentially, there are no people in the model. Earth system models don't directly interact with people. I mean, the emissions of carbon are there in the model, but they are prescribed. So this is a challenge for the next few years, next 10 years, to actually include people and how they interact with the Earth system and how that feedbacks into the energy balance. So we are going from this concept of an energy, only focusing on energy balance, into something that relates to people, which means that you have to think about impacts. How does the climate impact an urban area or people somewhere, or coastal areas, for example? So you're looking at these questions that kind of are not actually the original concept with Earth system models were developed. So we are going into a new, essentially a new way of thinking of how to use this climate model. So I will stop there and let Liz take over. Thanks.
Hi, nice to talk to you. As George introduced, I do a lot of different things that range from sort of studying the history of the human energy system to very specific measurements in the atmosphere. I'm just going to show a few slides to back up what Rao said. I know Rao sort of jumped ahead to saying the problem with models is that they don't have people in them, but of course models are imperfect or limited in many other respects, including in what I study, the aspect of climate science that I study, which is the impact of clouds. So I'm just going to show you a few slides for context, and then we can just jump for questions. So let me see if this works okay to share my screen, which we didn't actually test.
At the bottom of
yeah, I got it. I thought for a second that I could not share, but I can. So let me put this in presentation mode.
There you go.
Is that in presentation mode now?
Not quite.
You guys? It isn't?
It's not.
That's
there you
odd.
go. That is.
Sorry?
You're in presentation mode. We can see FAR, SAR, TAR, and AR4.
Exactly. So this is just a cartoon that shows you the improvement in models from 1990 to 2007. So remember, when you make a model of everything, which is what an earth science model is, you're limited by two kinds of uncertainty. The first uncertainty is literally not knowing how things work, which that's certainly the case with humans, a lot of biology, and lots of aspects of clouds, is that no matter how much computational power we had, we couldn't necessarily describe them perfectly because we don't know everything. But then the second limitation is the purely practical limitation of, we have to do so many calculations in order to advance a model forward in time by an increment. And you're limited, if you want to do a run of a reasonable length, you're limited in how fine scale you can be spatially in terms of how you resolve the model, because the increase in spatial resolution in the model not only increases the number of calculations you have to do for each time step, it also increases the number of time steps. It reduces the interval between time steps so you can calculate. Because if you look at this image, you can see your time step for the model has to be such that you don't have air moving from one grid cell to the next or to two grid cells further on in that time step. So as in what we could do in 1990 with much more limited computation, you can see it was pretty crude. This is supposed to be Europe. You can barely kind of see the outline of Europe. You can't really see the Alps. So obviously we're not going to get local weather right. As we advance to 2007, it's starting to look sort of more like you'd certainly recognize the continent of Europe now in this. That's 110 kilometers. That's still not sufficient for the kind of work that I do with clouds, where you're looking at features that are, you know, a kilometer across. Maybe they're 100 meters thick, which means you have to be much better resolved in order to understand what's going on within them. Okay, so I'm going to advance. So this is a slide of pretty much the best kind of models we can do now, and you'll see the resolution is much better than what I just showed you. But that's because we don't use these for the big assessment reports that Rao works on, because we can't run them for 100 years. These models are so computationally expensive that this project that Compare, they only ran them for 40 days. So 40 days in sort of real time is all they could afford to do before they had to go analyze these. So this project is called the Diamond Project. Of these 11 images here, 10 of them are models and one of them is Earth. And I want people to tell me which one is the Earth and which one are the models, and how do you know? So what do you learn from this figure? Like, does this say that models are sufficient? I know you're supposed to ask us questions, but I want to ask you questions. Like, this whole seminar is about the adequacy of climate models. So if you look at these images, knowing that right now we can still get only 40 days of run, you know, in a reasonable wall clock time, you know, we can only get 40 model days. Then we have to do this analysis. You know, the data are in many, many terabytes. One of these is the Earth. 10 of them are models. Which is which, and what else do you see in these figures?
Liz, do you want me to take a shot?
I want the students to answer.
Okay, students, go for it.
Even if you don't know, like, we always want our grad students to say something. You can ask an obnoxious question if you don't have an immediate insight. It's not a test. It's like an opportunity for you to look at data and see what it is and ask.
I'll guess. Is top left the real Earth? That's my guess.
No, but it's a very interesting thing that you're pointing out. You're saying top left is different from all the others, which is true. And so top left is actually fairly inadequate but it is, you did notice that there are differences, and the top left stands out in a way. It doesn't stand out because it's the Earth. It actually stands out because it's a particularly poor model, but it's a good observation that it's different. So top left is sort of too speckled, right? There's not enough pattern. There's like the spatial scale of these large scale patterns is very small. So it looks sort of speckled, and it looks different from all the others. But that's not because it's the Earth and the rest are inadequate. It's because models are quite different. And that model produces this weird cloud pattern. But that tells you right away, like, I knew exactly what you meant. You picked this one out because it looks different. And you can see the diversity. All of these are state-of-the-art models. And these are all run at very high resolution. So the picture I showed you before had the grid cells were 100 kilometers, the finest ones. These are typically like 4 to 10 kilometers size. So it's 10 times better than what I showed you, 10 times better than what's in the IPCC reports, but they still don't produce a uniform pattern. And these are 40-day initializations from the same initial state, so they shouldn't have drifted that much away from each other. You know, it's not like they're hundreds of years out, but you can see, like, the one on the bottom right has this kind of feathery pattern that's totally different. And clouds are the single biggest, you know, controller of our climate, right? Like, just a 10% change in cloud properties will be sufficient to the same effect as a doubling of CO2, right? Clouds are enormous controls on the Earth's climate. And so if you don't get them right, it's hard to get the climate right. And it's also hard to understand whether you're getting projected future changes right. So does anybody else have a quick guess? I don't want to take too much time because we'll cut into things, but
Is it the center?
you think the center is the Earth?
Yeah.
Is that an assessment based on psychology or based on how it looks?
Well, I mean, it looks the most continuous, like the clouds seem to have like the most continuous shape compared
It
to
is the center one, and which is partly a psychological thing. Like they could have been trickier and put it somewhere else. But it's also true that if you've looked at enough satellite images, so most people will end up saying it's one of the middle three, right? Because they look the most similar, those middle three ones. And they do look very similar. So yes, you're correct. It is the center one. That is the real Earth. There's something that's very intangible to define about why that cloud pattern looks more realistic. It's very difficult to characterize these patterns. I actually have a whole AI project just devoted to sort of using machine learning to develop classifications for clouds to try to explain, like, how would we quantify what's different about the top left and the middle one, which you guys both picked out as being something that was very different. And yet we don't really have the words or the language, even statistically, to explain why they're different, right? So, but anyway, so the point of this project, the point of this slide was to say, clouds are important. They're really hard to get right. They depend on very small scales of resolution. They also involve things we don't necessarily even know physically. Here is the best attempt we could make at a global model that is so fine scale, we can only get like a 40-day run out of it, not a 100-year climate change run. And they still don't produce the same thing. And out of two guesses, the one guy guessed an outlier, which at least shows that models are really different from each other. And the other guy guessed the center of the Earth, which is not random, right? So you have two non-random guesses that imply that models are not capturing the real Earth, that well. So that doesn't mean they're inadequate for certain things, but they're not adequate for everything. And we just have to recognize that, and sort of use them in the appropriate way. So yes, that is the Earth. And this is, which is reasonably close, but it's got its problems, right? There's way too big areas of cloud-free zones over the ocean. So just showing you a little image here just for fun. This is not the real Earth because we don't have continuous coverage from satellites like this. So a model is useful because we can do more things with it. So the models are pretty good. They represent actual hurricanes forming if you can run them at this resolution. It looks pretty realistic. That's the one at the lower left that I showed you. I mean, you wouldn't immediately say this is not the Earth if someone showed that, but if I show you 10 of them together, someone is going to pick out the correct Earth out of it. So they have a lot of features, right? They're useful. Presumably they have some guidance. They're not doing everything though exactly as the real Earth works. And then here's a project I actually worked on with Rao and Rao's postdoc, where we're looking now not at a global model, but at a regional model that's forced at the sides by the global model. So this snapshot is just over North America. What I'm showing you here is a brief period in June of 2005, where it's forced by our version of reality, which our version of reality is the thing on the upper left. That's kind of observations fed through a model to get the best information we can, but obviously that's not very good. So the thing on the bottom, the top left is reanalysis. The bottom left is radar-based observations. It's a data set put together by people who are merging the top left field with individual radar observations from individual stations. So that's the closest approach we have to reality, and it's only valid in the white area here. Not enough stations in the gray area. But in the white area, that's like the best thing we know about rainfall in the United States during this period. And then the four models on the center and the right are models run by Rao's group that are regional models, very high resolution, so we can run them for longer than 40 days because we're not trying to do the whole globe. There's a hurricane coming in, you can see that, right? So they all capture the fact that there's a real hurricane. But none of them are perfect, right? They don't exactly reproduce what's there in the bottom. So I don't know if you can see my pointer in the bottom left here. And in particular, they tend to spread the rain out over too big an area. So they get the average rainfall right. Presumably they get the change in rainfall right. There you can see that they tend to rain over much too large an area. So they have more drizzle over bigger areas. And that's the case even for the center lower model here is run at 4 kilometers. That's the best at the time that these runs were done. That was like about the best you could possibly do. And so this run that Rao's group did is really like clearly an improvement above the other ones. It's raining over much smaller areas. It looks the most, the one in the center, bottom center here is the most like the bottom left that we think is reality, but it's still not perfect. So that's just to keep in your head that there's always these intrinsic issues because we're trying to deal with processes on so many different spatial scales. We just can't capture them all. So now I guess we're on to the question period or whatever you want to do with it.
Okay, great. Thanks, Rao. Thanks, Liz. Terrific.
But just to also remind the students, like this kind of back-end work that was done by Rao's postdoc, you know, really carefully looking at all these different potential settings that she could use in the, you know, she's switching settings, she's changing how the microphysics are represented, she's changing the spatial scale, and then doing an analysis that says like, how are they different? How do we make statistics that describe whether they're different? Like, how do we even make a marker or a metric of goodness? That's hard stuff, right? We have to do that in order to use this tool in an appropriate way. So it's because of that care on the back end that we can make these assessments at all. So that's something a lot of incoming students have this mistake. They're like, I'm going to run a model and then I'll know what happens in the future. It's like, no, what you're going to do is you're going to run 10 models and compare them in order to quantify the uncertainty in the model that you run to tell you what happens in the future.
So we're getting a couple of questions, and I think I'm going to ask Adele. Oh, sorry, not Adele. If you don't mind waiting a bit. There's a different question. It's Ashley. Changes in clouds. Ashley, do you want to ask your question?
Yes, thank you so much for your presentation. It was awesome. I just had a question about the clouds and like what kind of changes you've seen throughout the past couple of years, and if there are like kind of direct indication of climate change and something that we can just see and like, oh wow, the clouds have been more dispersed over the years, if that's what you're seeing.
So we can't see that. The answer is that's a great question, and Rao should also answer that, his version of that answer. But it's the big worry, like how will they change? You could make a change that amplifies climate change. You can make a change that mutes it, that sort of mitigates it a little bit. So I don't know, is any of you guys from the West Coast of the US? So yeah, are you all Midwesterners? Or?
No, all over the world, actually.
So maybe England, could be England also, but certainly West Coast of the United States. There's this huge deck of low clouds that goes over the Pacific on the west side of the US and extends way out in the middle of the Pacific. So if you've ever been to Seattle, you know, it's kind of foggy and gray, even San Francisco, like behind you, like Ashley, behind you in your screen, you see the fog coming in San Francisco, right? So there's often this deck of low cloud. And that is a great big sun shield. It cools the earth, it keeps it cooler. So one of the big concerns is in some model projections, which people run these models to say what will change, that cloud deck kind of breaks up. And so suddenly, instead of having a nice big shiny cloud deck, you have a patchy one that lets more sunlight in, which amplifies. So that's a change that amplifies global warming. That's probably the biggest concern that people have, is that low cloud feedback that is sort of consistent in models, that there's a positive, what they call positive feedback. So you have reduced shininess of the earth, less cloud cover. So maybe people in Seattle are like, way more sun, but that's bad for everyone else. That's not easy to pick out of observations yet. You can try to look at the total reflectance and just actually ask if the earth's reflectance is changing. That I think is too hard to pick out of the noise. And in particular, what we want to do is we want to look at individual cloud patterns and ask if they're changing. And that requires us to even define what a cloud pattern is. And that's why we have this big artificial intelligence project, just to say, like, what is a pattern? You know, how do we even describe what a cloud looks like? You know, in that picture you saw of 11 different models, it's like, well, how would we make a metric that describes that pattern other than saying this one is patchier, right? You know, so what do we mean? What's patchy mean, right? So the answer is there's not a signal that's big enough to come out of the noise yet. but it's a real concern. So we're trying to make ways of studying it exactly to answer your question, to say, well, can we now process our data and see if we see any changes in pattern that are indicative of something? And can we then get any confirmation that the models are doing the right thing? But we don't know yet.
Yeah,
Rao, please go ahead.
Yeah, I agree with what Liz is saying. The best evidence we have about clouds changing or what we do on the humans affects the clouds is when we see huge amounts of pollution. That is like some cases in China, there were seen that deep convective clouds are actually affected by the aerosols you're emitting at the surface. And also when you have large forest fires, you can see the effect of aerosols on those clouds. And the third instance where we know that these things modify clouds is when you look at the ocean, there are ship tracks. Essentially, most of the ships use very high sulfur fuel. So you can see these things forming these contrails, and they look optically, they are very different from other clouds that you see in the marine environment. So those are some instances where you know it happens. But overall, as Liz said, it is still a scientific, not enough data to pick that out.
You can see the uncertainty issue. Like here, Rao says, look, here's a mechanism. If we add more pollution that basically seeds clouds, we would increase cloud cover, right? This is one of the principles of some of the geoengineering strategies, to throw up particulates and make more clouds. But on the other hand, the natural system may be trying to reduce cloud cover just from being increasingly warm. You know, we definitely know that both mechanisms, the more particulates producing more cloudiness, that's certainly something we see locally. We don't know what the global impact is. We don't know what the other effect is going to be. So we don't know if our more pollution is sufficient to kill it. Plus, there's other reasons why you don't want to be so polluted. So one of the things that makes it complicated to evaluate past observations to look for trends is because we will see a natural reduction in cloudiness just from the fact in the United States anyway that we got cleaner, right? So as we cleaned up all the coal plants under the EPA, we also removed a lot of sulfur dioxide, and removed a lot of other particulate matter that can help promote cloud formation. So we will see a net darkening of the United States precisely because we got cleaner. That doesn't mean it's a global warming driven change. And in fact, it complicates our ability to understand sort of a temperature driven change because we have this change in background aerosols. And, you know, if you're asking what is the change in background aerosols from the 1970s to the present, it's like, well, we didn't have great measurements in the 70s, right? So it's very, very tough to address these questions about changes by looking at a historical record that's affected by all kinds of complications. And remember, we've only really had decent satellite measurements for, you know, maybe 30 years now, which geologically is pretty short time.
Liz, can I ask, is it possible to tell whether clouds are getting worse or better over the 30-year period where we do have some observations?
So I haven't seen anybody produce something, and again, Rao may know more than me. I haven't seen anybody produce something which is definitive on mechanisms. There is some arguments about albedo that might be above the noise, but like I said, those are complicated by the fact that pollution is decreasing in some areas and increasing in others. So even if you just look at the Earth's albedo, I don't know how you would untangle those concepts. So the only way that I could think of how to do it was to look really hard at these low cirrus decks. And this AI thing seemed like a good application for AI to say, we just want to find some way of evaluating these historical trends. But even the cirrus decks over the ocean, they're also affected by pollution, you know, because it's not perfectly clean air. So we don't have a complete test case. God didn't give us a planet where we could test all these things independently. Which is why, again, why we have to rely on models in part, but figuring out in the world that is approaching us, so in your sort of academic generation, how are we going to take models, which are pretty good, but not perfect, and combine them with observations to, you know, a model is basically a prediction of an experiment. Now we have the experiment playing out, we need to combine that with a model to try to understand what's going on. And that's a very, very tough area. Historically in climate science, the model people and the observation people have been very separate.
So, Rao, comment?
I mean, the only maybe reasonable evidence has been people trying to measure the droplet size within the cloud. So this is recent, like you have some satellite data. So they are showing that some areas that are affected by pollutants, you can see the droplet size of different sizes. So this is just, it's not at the scale that we want, but there is probably data building that we could see that pretty soon in some papers.
But in terms of changes in the Pacific cirrus stacks,
Yeah.
I don't think that there's anything above there's no signal above the noise yet.
Yeah.
But the models also make that very nonlinear. So some of those, you've seen Tapio's papers, right? The ones that argue for a collapse of that whole cirrus stack, but that it's not a linear gradual thing. It's more of a, tipping point kind of thing. But then again, we don't know if that simulation is accurate enough. So it's just a prediction right now, or a projection by some, but not all models.
So
But
Fizz,
it's why we care. It's why this is still a field, right? We're not done understanding this problem.
no, I have the sense from what you guys are saying that there's still a long way to go. And we want to get to that in a minute. Fizz has a very interesting question about cloud cover. Fizz, do you want to ask that question?
Sure. Thank you so much for the presentation. It's really interesting how things have progressed in terms of simulations. So my question was, did you see any variation in the cloud cover during 2020 and 2021, since there was a lot of quarantine and people were practicing isolation and there wasn't much movement within, there wasn't much people activity during this like 12-month period. So was there any visible change that you guys observed? Thank you.
God, I might defer to Rao on that one because I don't know about the cloud cover. I know there was very significant pollution changes in many parts of the country just during lockdown, especially in India. People saw the Himalayas that hadn't seen it, in 20 years. I used to live in Los Angeles, and the pollution has a very short time scale. So once people stop driving, it clears in a day or so there. So, so that was quite dramatic. Whether we've done the study yet to see whether there was an actual cloud cover. So in that case, it wouldn't be a temperature driven change. It would be an aerosol driven change. And I have not seen any studies that come out, but you're right. It is something that could be done and is an interesting natural experiment, probably especially in Southeast Asia and the Bay of Bengal.
Like I'm in South Asia right now, sorry. So what I observed was we had a lot of, our visibility improved a lot. Like we could see we could see to a lot of distances, like things we weren't able to due to pollution. So that was kind of a physical observation that we as residents or just common citizens observe. So that's why I asked the question whether
it's a super good question, because it was very strong in India over very big areas. India would lock down pretty hard. So whether that made a manifest, so the pollution is what you're seeing with the pollution is you're seeing the actual particles themselves. Those aren't cloud particles. That's secondary aerosols that are formed from gas phase pollutants. So the question is whether the reduction in secondary aerosols made a difference to clouds downstream, which is a very good question. And I have not seen any papers out, but that doesn't mean someone's not working on them right now. Do you know, Rao?
Yeah, I mean, I also saw mostly on the pollution reduction. It's visibility is mainly in places like India is essentially it's lower atmospheric particle pollution and fog. There is improvement in the fog. There's less fog this year in India because of less pollutants. But cloud cover, again, you realize that 70% of the planet is ocean. So when you're looking at this data set, you have to look really for small regions to see these immediate impacts, like a reduced.
The lockdown might not have been long enough to get good statistics also, right? I mean, so the pollution clears fast. So you can say, look, I see change in visibility, but because clouds are so variable anyway, like in order to say this is statistically significant, you would need, you didn't lock down all summer, right? I don't know how long the signal was.
Yeah, I mean, it's actually the last year there was this several, maybe 3 months lockdown last.
Well, that would be enough for data. That's a really good project idea, actually, to see what you can see from that. shipping, you definitely see, like right after 9/11, when they shut down air
yeah.
traffic, they could see obviously the contrails go away. So you could quantify the effect of aircraft fairly quickly, just because a couple days of not having airplanes was enough to show that.
Here's a broader question for you guys. Did the pandemic have any effect on climate change?
No.
Well, it reduced CO2 emissions temporarily, just because travel slowed down and the economy slowed down. So there was a dip in, or at least a reduction in growth of emissions. That's probably gone away now. So no, I don't mean, unless people decide they're going to stay home forever and stop traveling, I don't think it'll have made a big
No.
difference.
Rao, I sensed you had a comment.
Oh, no, there was no change. I mean, I think it was a very temporary dip in emissions, and they are probably back with a vengeance right now. Maybe
Yeah.
as the economy all over the world spins up over the next year, we may increase emissions and compensate for that. So these are long-lived gases, so it really doesn't matter. One season.
I did think the visibility, so the improvement in visibility in Asia had a potential to have political consequences, because people realized, you kind of, it grows, the air quality gets worse gradually, and people forget how it was in their they never saw their parents' day or their grandparents' day. So seeing this change where suddenly you're like, this is how the world could be, can produce political action. So it could have indirect sort of social consequences where people are like, I've seen clean air, I demand clean air again. I know that clean air is possible, right? It was a demonstration of possibility in some places.
Yeah, pretty
A
interesting.
lot of people who took pictures on a clean day, comparing them to the time when they were dirty air. So they look so much better because the blue contrast of the sky is so all the selfie people are all riled up right now. They want clean air. Hopefully they'll convince their governments.
That's a really interesting point. Axel had an interesting question. Axel, do you want to ask that question about the models?
Sure. I was just wondering what's needed to improve the models in general, like in the next few years.
I'll let Rao answer that first if he wants.
I
We'll have
mean,
different answers probably.
the resolution is actually one part of it. There are some physics. The coupling between the biosphere and the atmosphere is still probably not that great. The clouds, maybe if you resolve the clouds completely, go below 1 kilometer, maybe you can solve some of the physics issues with the cloud, but you don't know. You have to try that. And the biggest challenge for doing that is that we don't have enough computational resources right now to actually run the model for long enough to evaluate. So the model that Liz showed right now runs at 3 kilometers. It's called cloud resolving, the one that is operated by the Department of Energy, but 3 kilometers is not really resolving all clouds. But let's assume that it only runs for 4 months. Like say I want to run it for 40 years. That's an immense amount of computing time. So they are making these models into GPUs and all that kind of stuff. So maybe AI will speed that process up. So there are some issues on physics. And as Liz already pointed out, running the model, one model once is completely waste of time. It's just a realization. So there are so many uncertainties. You want to run an ensemble. So right now, the best we can do an ensemble is 20-member ensemble. That is called a large ensemble simulation. There's the 100-member one right now. We would like to run it for 1,000. So how do I characterize the uncertainty in these models? We may never know every aspect of the physics. So we really have to play with the uncertainties to understand how important are those to the model itself and how we can go about reducing them. That requires that we run tens of ensemble, not hundreds of ensemble, not tens or 2 or 3 or 4. So that is a huge challenge in front of us. And I think AI probably will help. We don't know. GPUs may help. We don't know. The way our models are written, they are not suitable for running on a GPU machine. They are suitable more for a flat CPU. So a lot of things going on. But the main challenges are still some unknown aspects of the Earth system that we don't know what is. Some sensitivity is mainly coming from coupling. You couple ocean, land, and atmosphere together with various other processes, you may discover that there is something you're actually missing, or some coupling mechanism that may be interesting to understand better. So those things are not yet fully understood. So computational and ensembles in my mind, and then some questions related to physics and chemistry and biology, which Liz works on, so she may answer that.
I was going to say that when we've done, so some of the students in this project that I'm on, this cloud project, we mostly focus on high clouds, not the low clouds that are the most important. So we say we're studying like the second or third most important change in the Earth system, not the most important. But they found that even at very high resolution, there were big differences between the models that were due to the choice of the microphysics. So the decision about when water condenses into a cloud droplet, when it freezes from a droplet into an ice crystal, those were very consequential. How you represented that evolution of droplets and ice crystals within a cloud was almost as important as the resolution. So even if we have infinite computational power, we still need to figure out how we represent those processes, which we can't resolve. You know, you can't resolve how one molecule sticks to another one in a simulation. So I honestly think the challenge is going to be, you know, we did as good as we could with projections. It was enough. It was, you know, the science that came out of it is all very sound. We have uncertainty ranges on things, which are probably pretty reasonable. Now, as we go forward, we're going to start seeing actual changes happening. And the question is, how do we use those changes to help inform the models? So there are a lot of people trying to use AI techniques to improve the representation within models of all the processes that are parameterized, you know, the things that we can't really capture, like, you know, which are a lot of the cloud processes and the convection that leads to clouds. And people are trying to do that now with the existing historical record, but as changes actually start getting manifested, then we have even more data points, because now we'll see things actually change. But how we bring data and models together is sort of the next frontier. Whether we're assuming that the data is from sort of an unchanging state, or whether we're actually trying to capture changes that have happened in the world, it's still, it's very cutting edge and new to figure out how do you directly inform a model from raw data. It's very hard to do that. There's several groups doing sort of big efforts right now. Department of Energy, I assume, is very interested in this, but it's not clear, you know, it's in its infancy. So whether you can produce a better representation that way, that's not clear yet.
But the first step might be simply to do a comparison. Run a model of the last 5 years, compare it with what happened in the last 5 years. Is it good? Is it bad?
Well, that's what we have. That's what the diamond is showing you, you know, that they're still quite different, right? So, you know, there's ones you can start to be smarter about saying which ones appear to be better and why are they better. And, you know, can we, at least in our reports, can we weight the better ones more than the weak ones, or can we understand what features of it that make a model better? But, you know.
I also think that the issue with the climate models, like run the last 5 years, that's kind of a weather model timescale. The models itself were designed to do a longer term climate averages. Yeah. But right now the resolution of the models are coming down. So a lot of the models are at the range where you could also use as a weather model. I think that that's transition that's going on right now, that there is this continuum of models goes from weather to climate. And there are issues in like subseasonal, seasonal is a challenge. Days may be okay, but years. So you're trying to do what you're trying to produce. If you're trying to predict temperature 5 years from now on a summer day, that's much harder. But if you're trying to predict the statistics of what it would be the median and what would be the range of temperatures, that is possibly possible. So these are there's generally gets into a place where you're mixing weather statistics with climate kind of thing. And that's a challenge. I mean, is there one continuum model that works from today to 10, 100 years? That doesn't exist as of now. So the problems, the models that predict weather are very initial condition focused. So the idea is if you can get as much data as possible into the model, for today, I can predict the next 18 hours as best as I can. So there's a lot of effort goes into building those initial conditions for those models. Whereas climate models are called boundary condition problems. So the idea is the climate model is that they're not so dependent on initial conditions. That is what the state of the Earth system is right now, but rather how it is forced into the future, like the sun is changing or the greenhouse gas emissions are changing or something like that. So the external forces to the system. So it's a different kind of model. The climate model was built to do a boundary condition problem, whereas the weather models are built to do an initial conditions problem. So we are trying to merge these two kind of things together right now. And there are several models, and NOAA is building a model system that can work all over the globe around 1 kilometer right now, which is east here. The Europeans are building one. So there are a lot of efforts to build these things. So then we'll have to see how this model behave on a initial conditions phase compared to a longer term predictions. There are huge challenges on predictability as you go sub-seasonal and seasonal and interannual. So it will be a while before you can predict the weather next December 31st. So it's not, yeah.
Sam brings up a new subject. Well, let him ask his question. Sam, do you want to ask?
Yeah, sure. So my question is, you guys have a pretty sophisticated models for cloud coverage. Could these models be used in sort of studying or predicting how geoengineering would impact the climate?
Well, sure. There's a whole group that does that. They're trying. I mean, it has all the same, the same uncertainties as in a regular climate prediction. Is now you tinker with the Earth a different way, and you say, like just as words have uncertainties if tinkering with the Earth by adding CO2, and then you say I'm going to tinker with the Earth by putting in sulfuric acid aerosols into the stratosphere, and you have different, but similar magnitude uncertainties in that. But yes, it is a big project. It is ongoing. They do exactly that. They take the models, they run them with added CO2 to simulate the future. Then they run them with added CO2 and adding enough sulfuric acid aerosol to counteract some or all of the temperature increase. And then they do these comparisons. And if you want to get involved in that, I have one student who started to get involved in it, but it's a huge amount of unstudied stuff still, right? It's fairly recent. There's big archives of data. They do these big multi-group model comparisons, and then suddenly you have terabytes of data, and the grad students have to pick through it and answer questions. So, my students started and then dropped a project to look at how the Asian monsoon changes under geoengineering. Like maybe you have a geoengineering strategy that fixes global mean temperature, but it messes up the monsoon, right? These are kind of things we want to know. Does the model represent the monsoon? Well, no, not perfectly, but you could at least look and say across all these different models, are there any consistent changes, or are there just lots of big changes? And then maybe we're uncertain, but we're scared because it's not good to change things, right? So those are very good projects for grad students. I don't know if you guys are all in grad school already. Those are totally reasonable kind of projects to be asking. And so you're not going to get the answer, but you'll get uninformative answer, right? So there isn't right now a good answer to say, if I add stratospheric aerosol sufficient to make sort of a global temperature cancellation of global mean warming, are there specific regional effects that are on precipitation systems that are really bad? Like 1 billion people depend on their rainfall from the Asian monsoon right now with rain-fed agriculture. Messing up its timing is a huge issue. There's a lot of
sorry.
Go ahead.
I used to have a,
Sorry, go ahead.
If you have a answer to the first question, I was going to ask a squishier follow-up question, which is, do you now think that conducting research on geoengineering is a moral hazard?
Okay, first question I will answer to the second. The first one, the interesting thing that is probably the most interesting thing in geoengineering right now is people trying to build what are known as cloud chambers. One of the biggest questions for cloud aerosol interactions is how aerosols interact with clouds, and the microphysics question. So one way to do that is build a cloud chamber or a box where you can actually form a cloud. So there are several people trying to build these clouds in a box and then change the parameters. And like I put more aerosols, I take the temperature, does it respond the same way? So essentially, because we cannot do experiments on an open system, we are building a closed system where we can actually do these things. This is probably a very promising way to understand the microphysical part of the cloud system. So that's that thing. The moral hazard part, I think Liz already answered that. I go to conferences in India and China. They always say there is a lot of interest in geoengineering. It is mainly because they think they have succeeded in cloud seeding. There is so much money going into cloud seeding in India and China. That's amazing. It hardly works, but people have the belief that you can seed clouds. And there are companies that promise you that they can seed clouds to bring rains. So there's a lot of money going into that. They also think the cloud geoengineering is a potential pathway. A lot of people think of it right now. The thing comes up saying there will be winners and losers. So who are the winners and who are the losers when you do a geoengineering is a really, really tough question. And I think it is not a good thing to pursue, but that's it. But that's my opinion right now. Yeah.
Liz, any comment?
I guess my concern about geoengineering is twofold. One is just getting it wrong in a way that has immediate bad consequences. And in this stratospheric geoengineering is a problem because stuff stays up. I mean, the whole reason stratospheric geoengineering is cheap is because stuff stays up there for years. So that also means if you do something and you're like, oh, that was a mistake, I didn't really want that, you can add more, but you can't change it, right? So you're kind of stuck with the consequences of your decision for several years. Whereas I'm not sure what China is trying to pursue. They're probably trying to do stratospheric stuff just because it's cheaper, but there's also proposals to try to make more cloud cover, low in the atmosphere. And that's something that if you make a mistake, it goes away within days. So it's less problematic for that reason. But then the flip side of all this is if you're geoengineering in order to not fix your main issue, which is the rise of CO2, even if you geoengineer perfectly and, whatever solution you have has no losers, only winners, and everything is great, you've still basically, what I call put the earth on life support. You're now depending on this repeated action in order to keep it habitable. And maybe if it's stratospheric, you have to repeat that action every couple of years. And if it's low down in the troposphere, which is safer in one respect, then you have to keep repeating it every couple of days, right? Basically continuously. And I just don't trust our ability to do something reliably for hundreds of years in the future, Like people who talk about, well, they're going to geoengineer the way out of the problem. I'm like, I don't trust my government enough to be competent enough to do that. And then you put yourself on life support, you can't forget to have electricity one day, then you're dead, right? So the real terrible consequence is stopping the geoengineering and then getting the full impact of realized climate change happening in years, rather than hundreds of years. That's just unsurvivable. It's already too fast, right? So I think you just put yourself in such a danger zone by depending on something that's easy to screw up.
Interesting perspectives. Noah, you had it. We only have 5 or so minutes left. Let's try to get to a couple more questions. Noah, you were asking about building solar panels over small bodies of water. Do you want to ask your question?
Yeah, sure. I just heard our panelists yesterday mention, the idea of just building solar panels over some bodies of water to reduce evaporation. So I was just wondering if you guys have heard of that strategy and if you think it would be effective or efficient.
Why would they want to reduce evaporation?
I think it was for their water sources, so they're able to
like just trying to keep reservoirs from drying out.
Yeah.
So that's a different problem from this sort of, and then we'll make them solar panels. Basically anything large scale is super expensive. I watched someone do a calculation once, or read the calculation where they talked about just replacing Arctic ice sheets with ping pong balls, that are white and shiny. So we're like, oh, we can just solve this one small part of the Earth's albedo problem with some artificial material. And they counted up the total cost of doing that, and it's staggeringly prohibitive. Like, the Earth is so big. Could you tarp over a single reservoir? Sure, but even that would be really expensive. And the idea that you put solar panels on it is just like, there is no, people have these portmanteau solutions where they're like, not only, is it a tarp cover on it's like a swimming pool cover, but I'll also put solar panels on it. It's like, look, it's already complicated and expensive enough, we don't have a shortage of land. People who worry about putting solar panels, on top of your head, it's like, we don't have a land shortage. That's not our problem. Our problem is that solar panels are really expensive. We don't need to say, like, once I make a tarp, I can put solar panels on it too, because why not, right? We've got plenty of desert out there. If you're in California where it's dry, we're not stuck. Lack of land is not yet our problem, at least in the US. Maybe Bangladesh is a different issue, but all of these solutions that seem so practical, like, once you scale them up to geologic scale, you realize they're really expensive. The Earth is a very big place. A reservoir is a very large thing. It's not a swimming pool.
Rao, comment?
Yeah, I mean, I think it's been a solution generally proposed for where there is a shortage of land, like some places in India and South Asia, maybe other parts of Asia, where land is the biggest constraint for renewable energy in India and other places is actually land.
Yeah, that's true. It's not the US. The US is particularly rich in
US
land.
is
I agree. Different problem there.
There could be a solution there, but again, as Liz said, people don't think about how big these things are. Count all the rivers in India, for example, and cover them by solar panels is not trivial. But yeah, localized solution, I think, for a pond somewhere that you want to preserve water for a farm or something, I think it makes sense. If it is cheap enough.
So
But people don't really know. If they look at Lake Michigan, we're still not sure what will happen to lake levels.
Yeah.
Because you just jack up the water cycle under climate change. So you have more evaporation, but you also have more rainfall. It's not clear what happens to individual locations. And for Lake Michigan, right where we are in Chicago, the last couple of years have had historic highs, and the lake has been so high that it's been eating away the infrastructure. The paths are covered over. People can't bike on the bike path because it's underwater. So the problems in California are not, that's because, we have been seeing big droughts in California. Whether those are climate change induced or natural, it's not yet totally clear, but California does go through these big drought periods. So that's just lack of rain, right? There's just not enough water coming out of the sky in that case. Basically, if you live in a Mediterranean climate with seasonal rainfall that's already semi-arid, that's just not a good place to be under climate change.
So where is the best place to be?
Probably Chicago, I think, middle of the continent, not subject to sea level rise, big freshwater source, good infrastructure, plenty of land, relatively wealthy. We also, in Chicago, we don't really have many natural ecosystems left. So in the Midwest, we don't have to mourn the loss of our native wildlife because we kind of already wiped it out. So it's true. I mean, like, we just have corn, so we can adapt the corn.
Rao, a comment?
Midwest. You're in a good place. Yeah. I agree with everything Liz has said. Yeah.
But places, my backdrop here, that's not Illinois. So
True. Well, we have a few of the fellows, as we call them, are in Illinois. Lots of them are elsewhere around the country. So, yeah, it's an interesting question. I'm looking at the clock.
You don't want to be on the coast? you don't want to be in a semi-arid place because for whatever reason, the models have a lot of uncertainty and precip changes in semi-arid places, and some of them get drier. Like most of you get more rainfall, but some, at least in many projections, the semi-arid places get drier, and you just, so it's uncertain. But you know, places that are already on the edge water-wise, it's just not a good place to be. Places that depend on seasonal storage of snow, which is like California where I grew up, really terrible idea now, because the snow goes away and you just don't have enough reservoirs. Like Rao said, places that are so crowded that it's hard to implement solutions, you know, that's bad for other reasons. You're just constrained. If you're in Bangladesh, you just don't have the real estate to put things up.
So I think that's a good note to end on, a good question, maybe not a good note, but a good question to end on. Where's the best place to be for climate change? And I'm looking at the clock. We're already 2 minutes over, which is fine. We always allow some time to slip over. But maybe we ought to adjourn. We've had a very active interaction with the students. Thank you, fellows, for asking the questions. I'm sorry we could not get to all of them. But you've challenged our panelists in ways that I think they appreciate. And I think I can speak for all of us in saying that we've learned a lot. So thank you, Rao, and thank you, Liz, for being with us.